P-adic numbers are numbers with base p, where p stands for a prime number, like 3-adic numbers and 7-adic numbers. To express a number, say 530, in decimal number system, we express it as 5 into 10 raised to the power 2 plus 3 into 10 raised to the power 1 plus 0 into 10 raised to the power 0. More generally, we express a number as 10 raised to the power n times a of n plus 10 raised to the power n minus 1 times a of n minus 1, and so on and so forth, where a belongs to the set of integers ranging from 0 to just 1 less than our base, in this case 10. So a belongs to 0 to 9. Similarly, in p-adic number systems, a number is expressed as m of n times p raised to the power n plus m of n minus 1 times p raised to the power n minus 1, and so on and so forth. And in digital form, it is written as m of n minus 1, m of n minus 2, extended indefinitely towards the left, whereas in decimal number system, numbers can be extended indefinitely towards the right. Now let's take an example of 5. 5 can be expressed as 101 in two-adic numbers as displayed on the screen. A metric is a distance function which takes in two values and displays the distance between the values as an output, and distance is always non-negative. So if the values are 3 and 5, our output would be 2 in Euclidean metric. A set of elements which has a metric is known as metric space. So from Euclidean metrics, we have real numbers as metric space. So a metric is just the absolute value of difference of two numbers, and absolute value of a number can be defined as its magnitude, or if all numbers were represented on a number line, then its distance from 0. More formally, we can write this. But this might not be the only reasonable way to define absolute value. So we know by our knowledge that any number alpha can be expressed in the form displayed on the screen by factoring out all the powers of p, the base or the prime numbers. So in p-adic metric, we define the absolute value of alpha as p raised to the power minus n. Isn't that amazing? So if I take 3-adic numbers and find the distance between 20 and 14, I will find it to be 1 by 3, and the distance between 5 and 4 would be 1. So 20 and 14 are more closer than 5 and 4 are in 3-adic metric. Isn't that amazing? But is our p-adic metric valid? For a metric to be valid, it should satisfy the conditions displayed on the screen, and I leave the challenge of testing our p-adic metric on you. Addition and subtraction in p-adic is similar to addition and subtraction in decimal. Let's add 4 3 to 2 1 in 5-adic. To do so, we first add 3 and 1 to get 4, and add 4 and 2 to get 6, but 6 is not in our digits list, so we obtain 6 by adding 5. To write down 5, we add 1 to the next place to the left, so we have 1 1 4. To subtract 3 4 from 4 3, since 3 is less than 4, we carry over 1 from the left column and add the base 5 to 3 to get 8, and 8 minus 4 is 4, and 3 minus 3 is 0. To obtain negatives in 5-adic numbers, we subtract 1 from 0. To do so, we carry 1 from the leftmost column and add 5 to the right columns. So this becomes 5, then subtracting 1 becomes 4, this becomes 5, subtracting 1 becomes 4, and so on and so forth. So this becomes 5. 5 minus 1 is 4. 4 minus 0, 4, 4, 4, and so on. And this can be expressed as in this form, and this is equal to minus 1. Therefore, adding all the powers of 5, we have minus 1 by 4. Isn't that strange? Similarly, adding all the powers of 2, we have minus 1. Consider this strange identity and think what will happen if I increase n to infinity, and note that term in mind. Now have a look at this. Now can I say in p-adic? Therefore, isn't that strange? So we haven't done anything tricky. We came to define new ways of looking at numbers and obtain useful results that seem to be impossible. And that's the beauty of it. And p-adic numbers prove that maths is something beyond just a play of numbers.